Greetings, EXAFS folks. What I'm going to talk about now is, for a little while, is some general remarks on analysis and how to think about disordered systems. And this talk will be a little bit different from my previous ones because this is going to be using Mathematica mostly. But first I want to say some kind of general remarks. First off, when we talk about disorder in EXAFS, it's means something a bit different than what you would mean in diffraction and the like. Um, I guess one thing I wanted to say before then is that the description in terms of modeling the distributions and things is actually rigorous. It may not seem like it, but it is, and I can explain it. There's a lot of stuff that's kind of done ad hoc, like assigning different atoms into different shells, but actually there's a rigorous basis for it. So what do we mean by disorder? Well, we can have, for example, a perfectly ordered crystal in 3 dimensions that is, from an EXAFS point of view, disordered because there's a wide distribution in distances to the atoms in a group or a shell. That's what we would typically call disordered, even though from a macro or a 3D point of view, it's not disordered at all. It's just what it is. Okay, so you have to be aware of that kind of jargon. And conversely, you can also have a situation where things are perfectly ordered from an EXAFS point of view. You have a bunch of atoms at the same distance, but it maybe it lives in a solution or an amorphous solid or something, and there's no translational order. So from a diffraction point of view, it would appear disordered. So there are different ways of looking at it. But the way we use it in in EXAFS is in the radial sense. Okay, so in this business, and what I'm going to talk about is an approach that is, in some sense, an extension of the original Stern-Sears-Lytle approach, but broadens it a bit by introducing, it corrects some errors in their stuff, and also generalizes it using parameters or mathematical ideas called cumulants. Okay, so we describe the distances and the numbers of atoms. I'm going to highlight this if I can. They're described by a probability distribution, P of R, little p. Here we've divided out the coordination number of the shell, so little p is normalized to 1. This is based on a paper I wrote in 1983 as a student, but it's still quite useful. As usual, we require that all the atoms in a shell are the same atomic number. That is, in the EXAFS equation, when we're summing over a shell, we're taking those to have the same atomic number because you want to assign the same scattering functions to it, to the atoms in that shell. So it's the same thing here. If you have different atoms at about the same distance, you put them in different shells. So it's just a logical grouping, and with no assumptions. It's just a prescription. That's how you want to handle it. Okay, a lot of the time I may refer to atoms of a different atomic number that are in about the same distance, and go into different shells. You may call them subshells, or I may, because like, if you have, say, oxygen and sulfur at similar distances, they would be in different subshells because they have different atomic numbers. Okay. And also, if you have even the same type of atom, but they're significantly different distances, then you want to put them into different shells. Now, what's the criterion for being very different distances? Well, there's a very good one, which is, as you can see there, if they're far enough apart, their signals will beat. That is, they'll have destructive interference between them. If you're in that regime, then you definitely want to put the atoms into different subshells or different shells. So the criterion would be if twice the maximum K value of your data range times the difference in distance between those two shells is, unless it's considerably less than pi, then you will want to put them into different shells. You want to put them in the same shell. Okay, if that delta R is bigger than that, then you want to put them in different shells because otherwise they will beat. So all the atoms in a shell you don't want to be beating with each other. If they are, you put them in separate shells. Okay, and okay, I have to keep my screensaver from coming on. In the okay, we use the single scattering EXAFS equation, and that's what all this stuff is referring to here that I'm going to be talking about at least. Okay, and so the relevant parameter there instead of path length is the distance, okay, to the atoms in the shell, and that's the R that I'm talking about. Now it's a little bit awkward, but true that in the single scattering EXAFS equation, the what is relevant is not just the distribution of atoms, the real one you care about, this P of R, but it's weighted with this 1 over R squared from the decay of the wave as it spherical wave as it goes out and comes back, but also this e to the minus 2R over lambda, and lambda is actually a function of k, which is the mean free path, and that's kind of awkward. And I have worked this out exactly, okay, if you know what lambda is, at least, and but what we use is the this what I call the effective distribution, which is I write as a capital P here, and it's our true distribution P of R weighted with this e to the minus 2R over lambda divided by R squared. Now, it's important to realize it's the effective distribution is what shows up in your data, okay? Your data doesn't really know about the true distribution in a sense. It's the stuff you determine from your data in the EXAFS equation is the effective distribution. So to determine the structure, we first characterize the effective distribution, and then we do make the small corrections, but significant corrections for certain things to find the real average distances. For example, the effective distribution is roughly 2 sigma squared over your average distance, less than the true distance. Okay, but you can work that out and correct for it. I have derived full expressions, exact expressions for these, relating these distributions. And I'm not going to show them here, but they're small corrections, but exact. Okay, the standard EXAFS equation is valid for small to moderate disorder, okay? And I'll define what that means. But it has to be extended if the sigma squared, the disorder in a shell, becomes too large, okay? So, for example, if sigma squared gets anywhere close to 0.01 angstrom squared, you should be thinking about cumulants. Now, if you're lucky, you may have your effective distribution be close to a Gaussian shape, okay? And in that case, you may be able to ignore them because cumulants higher than second are 0 if the effective distribution is Gaussian. But you certainly shouldn't count on it. And if you think of the distributions of atoms in most coordination shells, it's not Gaussian. You can broaden it out, and that's fine with a Gaussian smearing due to thermal motion, but it's still, that doesn't change anything. The actual shape descriptors, it's not really Gaussian. Okay, and if you have a highly skewed distribution, either positively or negatively, meaning skewed out or skewed in, and it doesn't have to be continuous distribution, you can get very significant errors in distance if you ignore them. For example, in the order of 0.1 angstroms, certainly several hundredths of an angstrom, plus or minus, if they're present in your data and you pretend that they aren't. So this is something you really have to be aware of. It's not some sort of weird boutique, obscure thing. You can get wrong answers if you don't pay attention to this stuff. Okay. So the approach that I took back in that paper in '83 was to expand in terms of cumulants. Originally, I was working it out in terms of power moments because I knew that there was something wrong with the usual description and I wanted to generalize it. Then I talked to John Rare, and he pointed out the existence of these things called cumulants, which are very wonderful, useful statistical descriptors of distributions. So they have many applications. And in fact, anytime anybody broadens a Gaussian with another Gaussian and adds the sigma squareds, they're in effect using a very nice property of cumulants, which is that cumulants add when you convolute distributions. It's very general and very useful. Okay, they're useful in many ways. So anyhow, the standard structural parameters in our most common form of the EXAFS equation are in fact cumulants. That is, are this e to the minus 2r over lambda. If we pull that out in front of we average that, that's e to the c0. When I say pull it out in front of an integral, we're doing an average, that's e to the c0. Or you take the average r is the average distance, that's the first cumulant. And our familiar sigma squared, that's the second cumulant of the effective distribution. So these are these really different names for things you've been using all the time. But the nice thing about this description is it generalizes. You can write a general thing for any distribution to any order using the cumulants, as long as the cumulants expansion converges. Okay, and if the disorder gets too high, you're better off making new groups of shells, regrouping the atoms into shells so that the cumulant expansion works for each of them. Okay, and you may be able to stick with the usual approximation in the EXAFS equation and just sum over shells. So that's fine. Okay, so the C0 and C1 and C2 are measures of the size, basically the scale of kind of the overall weight of the distribution, and the location, the centroid, and the mean square width, the variance of the distribution. Okay. So, and then the higher order cumulants, like C3, measures the amount of skewing. Okay, it's not the skewness because it's a dimensional parameter of order sigma cubed. And the C4 kind of measures how fat the distribution or skinny it is, how compact it is relative to a Gaussian of the same width, of the same sigma. Okay, so a useful rule of thumb is the following, that unless k times sigma is a lot less than 1, where k is effectively your average data range, could be the upper end of your data range, but say take the average of your data range, that times sigma, the sigma of it's your Debye-Waller factor sigma for a shell is much less than 1. If it's not that small, then you have to at least be thinking of that higher cumulants might be lurking in your data. And that's how I think about it anyway. They may be making significant contribution to your data. And if you're going to try to model it, you should make sure you include that. Conversely, if sigma is small enough, you're pretty much guaranteed to not have to worry about it. As long as the disorders, if it's small enough, you don't have to worry about it, whatever the shape of the distribution is. Okay. So I'm, like you, probably skimming through this, what I've written here. Okay, now here's an important point, that they may be there, but you may still get a good fit by ignoring them. Because when you include, say, a third cumulant in a fit, it adds a cubic term into the phase that you're fitting with. You're predominantly fitting with a linear term, the 2kr term. And you also may be shifting E0, which in effect adds a 1 over k term. So because of the parameter correlation here, if you have suppose you have a C3 that's physically present in your data, what it will tend to do is it'll shift the average slope of the phase, which shifts the apparent distance. Well, you could say, well, that's going to end up with a bad fit because it will also shift a constant part to the phase. But because of the parameter correlation, if you're fitting a delta E0 at the same time, a 1 over k can also kind of compensate for that. So you may be able to get a good fit because of this parameter correlation without including a C3, but you will still get incorrect error values. So I think a correct way to think about this is to view it, even if you're not worried about it for your parameter values, you should at least think about it in the context of your error bars. Your error bars are very likely, when you have a large disorder, considerably larger than you think they are, and then what the fitting program will tell you if you don't include a C3 and a E0 shift. Okay, so this really needs to be considered. Okay, out of sloth, instead of retyping equations, I decided to copy some stuff out of my book appendix. If you look in the middle of this equation here, I think I can point to it. Here's our basic EXAFS equation, but written instead of chi being the a of k times the sine of phi of k, generalized it to a complex quantity so we can manipulate it. And then we have the amplitude times e to the I phi of is equal to the number of atoms times b of k. Well, b of k is this. It's the scattering amplitude over k times S0 squared. That stuff factors out and in some sense divides out when you compare with other things. So we're interested in this stuff in this integral. And what you can do is these manipulations, and it comes down to this. Okay, all the structure of the in the EXAFS, in that distribution for a single shell, comes down to an integral like this. And the business end is in this guy. And we can expand the this in this cumulative expansion. Okay, so if you do that, what you end up with is all the even powers, at least in the case where we ignore the k dependence of the mean free path, then even powers show up in the amplitude and odd powers show up in the phase. Now, in my book too, I generalized this to account for any dependence of the inverse mean free path on k. So there's a general solution there. But to a good approximation, we can do it this way. So we end up with this expansion. And it's all worked out, and I'm not going to belabor it right now. But I consider it a solved problem exactly. If we know the inverse mean free path, which you can calculate, in fact, up front with programs like FEF. Same thing. We calculate the phases and scattering amplitudes and scattering phases, and the central atom phases also with programs like FEF. So there's nothing special about that. Okay, so we can do this, and that's described in my book. All right, in an appendix. Okay, so now what I want to do is do a little show and tell and show you how this works out, and then I'll conclude with talking a little bit about other ways to approach it. Part of this Mathematica notebook will show fitting with different distributions, and suggest one that's pretty useful for skewed distributions. It's pretty simple. And then I'll talk more generally about this. There are many ways to approach this using different distributions, and, both parametric modeling and non-parametric modeling. And I've got some ideas for some others too that I won't talk about right now. So our next thing here is this. This is based on presentations I've given at EXAFS schools. So what I'm going to show you here is just some sort of illustrative examples in Mathematica. Because my computer is doing screen capture, so a lot of its compute cycles are being burned by that, and it's not a terribly powerful computer. Okay, I just launched a Mathematica kernel and defined that function. Here's just a Gaussian function. It's normalized that I'm going to use. And what I'm going to do here is concoct some distributions that are relatively simple to show you how these cumulates emerge naturally when you're dealing with groups of atoms. Okay, this is just a thing that assigns values to different parameters. I'm going to take a 2 shells here. I'm going to let N1 with 3 atoms at 2 angstroms with a sigma squared of 0.005 angstrom squared. And the other one, I have 2 atoms at 2¼ angstroms at 0.005. Now these guys will show a clear beat. I can tell from the distances, so I want to show you that. So a beat is when they get significantly out of phase. Here's the functional form with the those numerical values. And here's a plot of the distribution. So I got 3 atoms in this one and 2 atoms in this one. They have the same sigma square. I'm going to do a Fourier transform of that. Here's the symbolic form. Okay. And that's with d values. Now here is how it applies to the beat. This is that expression I was showing for when you will show a beat. Here's the difference in distances, R2 minus R1, which was a quarter of an angstrom in the example shown. And so you'll get a, yeah, so the beat will occur at, in this case, exactly 2 pi inverse angstroms, or 6.28, etc., inverse angstroms. Right there. So if we're plotting this is k-space. And so those two things are going to produce an amplitude that looks like this. Now, what you can think of this is just the structural part of the amplitude. Any backscattering parts are factored out. Okay, so this is just the structural signature of the distribution of distances. All of this is structure. Okay, so we'll have a beat at, but you'll see this in your raw data too, in almost all cases. Unless the other scattering amplitude's doing wild things, you will see something like this. You'll see it come down, and there's a dip here. Okay, and I could weight this with k and get that. That shows it up a little better. But you'll get a dip here, and you can see this in your data. And in fact, you can even get that difference in distance off a graph. If you look at this, say it's 6.28, and go back through this, you'll see what the difference in distance is. That's if they're the same type of atom, so there's no difference in their scattering phases. In other words, like if these were 2 oxygens, you get something like this. And in fact, I've worked on systems like that with like ribonucleotide reductase, where you had short oxygen distances and some longer ones that were interfering. You can see it right in the data. Okay, this is the phase. Now the phase has 2 pi jumps in it, so that's not too useful. So, but we can quickly get rid of those. So here's the phase. And if everything were canonical here, the simple forms that you usually think of, this would be a straight line. But you can see it's not quite a straight line. It's got this kind of a jump in it. If you took out the slope of this would be 2k r, 2k times the average r, if it weren't for these things like beats and cumulants. Okay, we plot here's the logarithm of the amplitude, because that's the beat thing there, but also the derivative of the phase has the same kind of structure. It comes up here, and then it has a slight blip down in slope, and then it goes back up. That's the derivative of the phase. So the phase derivative and the amplitude have similar structure. Okay, so here's the average distance arithmetically. We had 3 at 2 angstroms and 2¼ I guess, and you work that out. Here's the average arithmetic average distance, and you may think that's what you should be getting. Okay, but in fact we have a 1/r² weighted average, which you would do like this, and in fact it's worse than that because you've got this exponential there that I'm neglecting right now. But you can see the actual distance you've determined is a couple of an angstroms shorter, 1¼ I mean hundredths of an angstrom, shorter than the real one. So these are things you have to account for in the when you're analyzing stuff. Okay, here's the 2kr curve. This 2k times the average distance. It's shifted down by pi because there's a 2 pi ambiguity here. That's irrelevant, but helpful for plotting. And here's the phase of the true distribution. So it comes up and then it jumps down and then it comes up like that. So these structural things, interferences, make a big difference to the actual slope of the phase. So you can see from this that if you were to like fit over some range like this, the average slope of the phase, which is the apparent distance, would be reduced. Okay, and that's the kind of effect we're talking about. All right, and here's the phase derivative over 2. Here's the average distance, r bar, and here's the average phase slope over 2, which is the apparent distance. So if you average this guy, you're getting a smaller number than the true thing. And that's really kind of the essence of the problem. Okay, but it's not a problem if you account for it. It's only a problem if you ignore it, and it's there. Okay, and here's the average phase slope. Okay, divided by 2. So this is the apparent distance. So it's shifted by about 0.025 compared to the real one. Again, if it's there and you didn't see it, well, you've got an issue. Okay, so I hope you see the point of that. Now, what I'm going to talk about here, I could go on a long way, but I hope you get the point. A lot of the time in real life, you end up with a truly skewed distribution of distances. That could be a discrete one, where you have a bunch. Here we had 3 at one distance, at 2 at another, but you can make a more complicated distributions. This is skewed, okay? And even if the beat weren't so pronounced, and maybe these distances were moved closer together, what you would see here, down here it's linear, and then it starts to curve. That's the third cumulant of this distribution coming in. And then at the beat, basically all orders of cumulants are important. Now suppose we made this distribution of atoms a little more compact, so the difference is smaller. If it were half the distance, the beat would occur out here at k equal 4 pi. Okay, in that case, there would be no beat over the range, but you would still see a change in average slope over the data range. Okay, so this cubic term would come in over this region, and if you fit this, and you can tolerate a little bit of error in your intercept, or compensate for it by shifting the E0 kind of artificially, which will happen in a fitting routine, then you will end up with errors. Okay. So what you at least need to do is include these effects in the error bars. All right. So if you have a skewed distribution, one that's skewed outward in particular, that's what this is set up for, is if you take there's a very nice distribution that's basically of this form. You take r minus there's a closest approach distance, r0, and then you take r minus that to some power, which is a parameter, and then you take e to the minus alpha times that. And these things are for normalization. It's a relatively simple distribution. It's kind of like a Poisson distribution that's shifted relative to the closest approach distance. And here's a picture, okay, our graph. And this is, as you vary this s, that's the exponent and the prefactor, you can see it gets wider, but it also shifts out. And if this is alpha is a width parameter, okay. And through the interplay of these things, you can get any sigma squared basically that you want, and you have to translate it back, but you can get any amount of skewing, positive skewing, and any sigma squared that you want. So it's essentially those two parameters mostly describe those two properties, and this is quite useful because it's simple to fit with, and it's flexible for modeling. Now, there's a paper, I think Dave Fazzini was the first author back in the day, and I contributed to it because I did some of the math. But anyhow, there's a you can do a closed form of that for the true distribution. But here I'm doing the effective distribution, modeling it with this. And it's working on this. But the point is, it's easy to work. The cumulants have a very simple form. The amplitude and phase have a very simple form. And it's a two-parameter fit. Instead of fitting with r bar and sigma squared, you could fit with these two parameters, say alpha and sigma. Okay, yeah, this is, in terms of power moments, it's very ugly. But in terms of cumulants, it's very simple. So that's the point. Here's the cumulants right here. I'll put those in a column. So here you are. Here's the different orders of cumulants. This would be the first cumulant here, and the second cumulant and third cumulant. In fact, they have a very almost trivial form here. So you can expand the amplitude and phase and fit it very easily with these two parameters. So I'm just suggesting that this is a useful way to handle certain kinds of systems in a parametric way, but it's simple. If you have a system where the cumulant expansion does not converge readily, that is, you require too many cumulants to effectively fit, then this can be a good one because this is convergent. All right. Now, the point is, if you can fit your data, and I'm going to stress this here, if you can fit your data within the experimental errors, okay, it's a good fit, okay, and it's physically sensible, of course. But the key thing is you still need to specify error bars on the distribution that you found. Otherwise, it's not of much use. You know, you can always, anybody can sketch a curve, and unless you say how well you can depart from that curve and still get a good fit, then that's not terribly useful. Okay. All right. So there's other approaches to this. This is basically a form of parametric modeling where you fit with different distributions. And I think using programs like Matt Newell's Larch, this should be fairly straightforward to do, I think. I'd use Mathematica because I've been using it for 30 years or something, and for stuff like this. And it certainly made working out the equations easier in recent years. I did the original stuff by hand. But you can fit with different distributions, and if you get a good fit, it's a good fit, okay? But you still have to generate the error bars. And there are many distributions you can imagine fitting with, including things like histograms, and I think people have done that. And, so you basically take an even space of things. You could use interpolated versions of those, Bezier curves. You can think of all kinds of things, but again, if it's a modeling a distribution, it's fair game if it works. But you have to be able to produce error bars for it. Okay, there are also non-parametric ways of doing things where you basically hand it a spectrum and it gives you back an estimate for your distribution. And hopefully with error bars, I guess I'm going to show you a simple version. We, a student and I think a fellow named Babinov, I think originally was applying this to EXAFS, which caught my attention back in the 80s. It was a little paper in a proceedings, but it was interesting, and we developed it further later on with my student, Gocha Kalashvili. So what I'm going to do here is to show you a simple version. What we did was more elaborate than this. This is kind of a toy example, but it shows you the idea. And I'm not going to belabor this. But what you can do is for basically calculate, what I did was calculate it as a function of k and r using pfeff, just running pfeff repeatedly, using in an automated way, of course. This is for building this kernel function using pfeff and assembling the results. You could do it in any language, just about. Okay, and then what it amounts to is a solving a ill-posed matrix inversion, in effect. It's a linear system, but it's sort of ill-posed, so you can use different ways of doing that. If you just use a singular value decomposition or something like that, then you end up with a result that is not positive definite, So it has the structure of a plausible radial distribution function, but isn't positive definite. I have some ideas for some better ways to do that now. That would be, and but what you can do is take basically this function, take an RDF, and if you take the dot product of that with this kernel, then you end up with your data. So it's a linear system and it's simple. So here's an example. Here's a synthesis, a fake RDF, okay, calling the true RDF. Okay, so we're making this, here's the data, we're going to make some chi corresponding to that. This particular one is for a single type of scatterer, and I don't recall which one, but then I can take the dot product of this thing with the kernel, and I get the chi that corresponds to that. So it's a fairly complicated distribution. You got a bunch of peaks of different types and the like. And then what we'll do is take this chi and we'll add some synthetic noise to it. And that's that. So there's some noisy chi. And then we're going to try to undo this and use something called, in this case, Tikhonov regularization. It's a simple form of regularization. And I won't belabor the math here, but there it is. And here's an estimate for the recovered. I think the colored line is the colored line is the recovered one, and the dotted one is the true one. Okay, you see some errors, but you expect some errors because there's noise in the data. Okay, but so you can say, okay, here's a version that we had cooked up, particularly Gocha, Kalashvili, using what's called Landweber-Friedman regularization, and you get some errors and stuff here. So the question is, how do you generate an error bar for this? Well, I wouldn't say this is a rigorous error bar, but what you can do is imagine generating a bunch of, in effect, fake data. If you know what your distribution of errors is in your data, then you can generate a bunch of, basically an ensemble of noisy chi drawn from that distribution of noise and errors, and create a bunch of data and then run those through this system. And this is what happens when you do that. Okay, so this is a sort of a plausible way to generate some idea of the uncertainties in your recovered data just by generating a bunch of fake data and running it backwards. And here's the some error bars that were derived from this for that. Okay, so it's not not perfect, and I'm sure they can find some errors, but you get the idea, and it works plausibly. It's reasonably it's a start on doing that. So going back to our original thing here, I wanted to mention regularization. It's a way of sort of stabilizing an inverse problem, so it doesn't, so that the result you get is in some sense stable with respect to small perturbations in the data. Okay, there are other ways of doing non-parametric modeling, and for generating RDFs, I think that Anatoly, in fact, I think, and some other folks have used some neural nets recently to and used wavelet decomposition to build a machine, in effect, analogous to regularization, but different, that when you feed it the data, generates a estimate of the radial distribution function that produced it. And this is done not through means like regularization, but by training it with a whole bunch of known data sets, where you can calculate this stuff and train a neural net to do it. Neural net's basically a generalized function that you give it. It depends on a bunch of parameters, and if you give it some training data, you can diddle the parameters till it gives the right answer, and then you hope from then on it gives the right answer when you feed it some other unknown data. And so that's the deal. Now, you could do the same kind of thing that I showed there in the regularization by generating synthetic data, vast quantities of synthetic data, and seeing how well it works, and generating an error bar for it. Again, that's not a rigorous error bar, but it's something. And with reverse Monte Carlo, the same kind of deal. In some sense, reverse Monte Carlo it's parametric in some sense and not in others. But basically, and it's a kind of a minimization strategy in some ways. Uh, but there are variants of that too that you could go a long ways with. So the punchline is that there's a lot of different ways you can model these distributions, but fundamentally, if you build a machine that generates from data an estimate for your distribution, then you have to be able to produce error bars on it. And we have some ways now that are actually reasonably good and could bear a lot more development. So summing up here, there's many approaches to these things, and but I think it should be at this point a sort of a basic a thing that people should know doing EXAFS is understand cumulants and the point of them. Should also know about beats and be able to understand their import in the data and the fact that if you ignore them and if they're present in your data and you don't pay attention to them, you can get significantly wrong answers. And you're better off including them. And even if you don't get different answers, you'll get more realistic error bars. So that's all I'm going to say for now.